Beta Gauri, I am not receiving any request from Vanchika Jain to let her in. Please tell her again to send me the request. I've sent you all a link for your attendance. Please fill that. This is for B2. I'm presenting the screen. Please let me know when my screen is visible.
It is visible, ma'am.
Okay. So, students, we are going back to lesson number 5 so that we can catch up with the practicals now. Okay. So, as I told you, I will be doing the instructions with you in the class, and you will be practicing the same instructions in CPU sim. Okay. Now, to set a platform for that, we will first talk about the types of control units today under this section, timing and control, which is section number 5.4 in your chapter number 5. Okay. So if you remember, we had said, as you can see on your screen, that the CPU contains three basic components, namely the control unit, the memory unit, and the ALU, that is the arithmetic logic unit. Okay. We have already seen the registers and the bus system in detail. The arithmetic logic unit consists of a series of circuits which can perform arithmetic operations and some other smaller circuits which are required to perform logical operations such as AND or etc. Today we are going to focus our attention to this unit that is known as the control unit. As the name suggests, the purpose of the control unit is to coordinate the entire operation of the CPU and hence also the computer. Okay, so please see, all these three units interact with each other. How does the control unit control the functioning of the entire CPU? There are certain signals released by control unit. Okay, yes. So this control unit basically generates some signals which are known as control signals. Okay, these control signals tell each unit what is to be done. Okay, let us see this with the help of a block diagram. We will have a look inside this control unit today. Okay, but before that, we will study what are the two different types of control units. There are two types of control units. The first one is known as the microprogrammed control unit, and the other one is known as the hardwired control unit. In the microprogrammed control unit, there is a program in the control memory, this memory, okay, which controls the functioning of the control unit. Okay, this program can be changed, and therefore it is easier to modify this kind of a control unit. However, in a hardwired control unit, there are direct connections, the wires which are fused with each other. So as soon as we apply power, automatically the circuits start working. But in this kind of a scenario, obviously, since the circuit once made is fixed, making changes are not easy. And every time the same things in quick succession, you know, will initially happen. Okay. So again, let me just go over these two types of control units. The first kind of control unit is called the microprogrammed control unit. There is a program in this kind of control unit, okay? The kind of programs that you write in Java or C++, for example. The only difference is that you are writing the program in a high level language, that is C++. This is a micro program. Okay, I will be talking about the distinction between what is a micro instruction, a macro instruction, and what is a micro program, therefore. So what is a micro instruction? A micro instruction is any instruction which is operated at the very basic level, for example, at the register level. Okay, so the most basic operation which we cannot divide any further, when that is specified by an instruction, that means an instruction that specifies the operation at the very basic level or at a level which cannot be subdivided any further, is known as a micro instruction. The operation itself is known as a micro operation. These are generally the operations which are, the very smallest of the operations, for example, which are done at the very basic register level. Okay. Now, any instruction that specifies a micro operation is called a micro instruction. Okay. And a program, that means a set of these micro instructions, would be called a micro program. Is that clear to everybody? Is that clear to everybody?
Yes, ma'am.
Yes, ma'am.
Let me try and show this to you through a so it will be something like this. Please see. So please see, it will be something like this. So micro operation specified by a micro instruction and a set of micro instructions becomes a set of micro instructions becomes a micro program. Is this clear? Right? Okay.
Yes, ma'am.
Right. So in a micro programmed control unit, what do we have? We have a micro program which tells the control unit how to work. Now, since you know it is easy to change instructions, what is easy to do? Is it easy to change the circuit every time, or is it easier to change a micro program? What is easier?
Ma'am,
Microprogram.
microprogram.
Yes. And so that is why, please see that this kind of a control unit has an advantage that it can be easily reprogrammed, that is changed. However, the hardwired control unit, as the name suggests, here all the connections are already in place. They are fused with each other. Okay, it is hardwired. Everything that is to be done is directly, you know, uh, implemented with the help of the circuit. Again, please see, for implementation, even this unit would require a corresponding circuit. Otherwise, how would the whatever we are specifying, whatever operations we are specifying, how would they be performed? But there is a layer. For example, you are programming in C++, right? So I hope you know that first that program is, translated into its equivalent machine language, right, into zeros and ones. And when finally it is translated in zeros and ones, only then it is executed, right? So for the first level which is done is that your program from the high level is converted into machine language, and then from machine language, that is zeros and ones, when you get the program, that transformation is done automatically by your compiler and the assembler. Okay, when you see, when you compile your program, what is happening is all the syntax errors and everything gets checked, and after that assembly of your program takes place. Okay, what is the job of assembler? It takes the program and converts it into binary language. Okay, so binary means machine language, right? Zeros and ones. So that zeros and ones, then they are then further relayed on to the circuit for actual implementation. If you have said 2 plus 3, for example, then a corresponding adder circuit will be invoked, and 2 and 3 will be passed in binary as inputs to that circuit. Okay, and whatever output is got, it will be stored back into the accumulator. Is this clear? Or the or from the accumulator then later to the variable that you have specified. Yes. So microprogrammed means they are not, we don't write the microprogram in a high level language, but in a machine language, obviously. But the idea is that this is easier to change because all we have to do is to change the instructions. However, hardwired control unit, we don't have a program to operate. Okay, we directly have to change the wires or the circuit to do any kind of change in this control unit. So this is an obvious disadvantage of this control unit, that it is not very flexible to change. But the advantage is that it is very fast. Okay, so this entire job of translation that I have told you takes some time from high level language to the machine language, and then it actually goes to the circuit where the thing is implemented. So the circuit doesn't take too much time, you know. How much time does it take when you switch on a, when you, switch on a fan for the fan to start moving? It doesn't take much time, right? So similarly, it doesn't take too much time for the processor to, that means for the actual circuit in these, let's say, arithmetic logic unit, which have to perform the operations to work. But uh, the translation takes time. Okay, so the advantage of hardwired control unit is that it is very fast. All we need to do is, switch on the circuit, that means give power, and it starts working. Is this clear? Is these
Yes, ma'am.
Are these two types of control units clear, and their corresponding advantages, disadvantages? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Now we are going to be focusing our energy to this kind of control unit, that is the hardwired control unit. Microprogrammed control unit is discussed in chapter number 7 of your book, but it is not there in your syllabus. So for your own interest, if you would like to look into that, you can, just read through. But for your, from your syllabus perspective, we will be looking at the hardwired control unit. Okay, so this is the difference. I've put it in the slide, and you can, this is also there in your book, so you can read it from there. Or can somebody just quickly go through this? Who will?
Dipali,
Yeah, okay. Thank you, Dipali.
you're welcome, ma'am. There are two major types of control organization: hardwired control and microprogrammed control. In the hardwired organization, the control logic is implemented with gates, flip flops, decoders, and other digital circuits. It has the advantage that it can be optimized to produce a fast mode of operation. In the programmed organization, the control information is stored in a control memory. The control memory is programmed to initiate the required sequence of micro operations. A hardwired control, as the name implies, requires changes in the wiring among the various components if the design has to be modified or changed. In the microprogrammed control, any required changes or modifications can be done by updating the microprogram in control memory.
Is this clear to everybody? Students, is this clear to
Yes, ma'am.
everybody now?
Yes, ma'am.
Okay. So now let us go and have a look at the control unit. This that diagram that you see on your screen is the block diagram of the hardwired control unit of the basic computer that we are studying in this book. So what is the basic computer? This computer with memory of 4096 cross 16 and 8 registers. So this entire configuration that we are studying in Morris Mano, this basic assumed computer that we are studying, is called as the basic computer. Okay, so even if you get this terminology of basic computer in your paper, it would refer to the same computer architecture that we have discussed in the that we have been discussing in this book. Is this clear? Right? So
Yes,
accordingly, if you remember, the instruction register we had said consists of how many bits? It consists of 16 bits and three parts, if you remember. So the first part is of 12 bits, which is actually the address part, then the opcode, and the final single bit is for reserved for the addressing
Mode
mode.
bit.
Yes, addressing mode, and it is called the mode bit. Okay, so please see now, uh, this block diagram will show you how the control unit actually works. Okay, let us first read it through and then I'll explain this block diagram to you. Yeah, Dipali, can you please read the screen
Yes,
for me?
ma'am. Control unit. The block diagram of the control unit is shown in figure 5.6. It consists of two decoders, a sequence counter, and a number of control logic gates.
Yeah,
And
please see.
instruct
I'm showing side by side, okay? So these are the two decoders. One is a 3 cross 8 decoder, then the 4 cross 16 decoder, and this is the sequence counter, and these are the control logic gates. Yeah, yeah,
an instruction read from memory is placed in the instruction register. The position of this register in the common bus system is indicated in figure 5.4. The instruction register is shown again in 5.6, where it is divided into three parts: the I bit, the operation code, and bits 0 through 11. The operation code in bits 12 through 14 are decoded with a 3 cross 8 decoder. The 8 outputs of the decoder are
are
designated by the
designated.
symbols designated by the symbols D0 through D7. The subscripted decimal number is equivalent to the binary value of the corresponding operation code. Bit 15 of the instruction is transferred to a flip-flop designated by the symbol I. Bits 0 through 11 are applied to the control logic gates. The 4-bit sequence counter can count in binary from 0 through 15. The outputs of the counter are decoded into 16 timing signals T0 through T15.
Yeah, okay, okay, okay. Let us first just see this part. Okay, let us first just see this part. Okay, so what is this? This is basically the control logic gates. These are the control logic gates inside the control unit. So what do they do? They basically perform the they perform the functions which are they facilitate the performing of operations which are indicated in the opcode of the instruction. Okay, so as you can see, this is the instruction register, and as I've just recapped with you that this is the address part, this is the opcode, and this is the mode bit. Now please see, the opcode, the address is directly being passed to the control unit. And what are we doing with the opcode? This is a 3-bit opcode, right? So if you remember, we had said that, I think there must be that slide somewhere. Let me just show you if I have that slide. So yeah, if you remember this 000 111, if the I was 0 and the opcode was 000 through 110, then it meant what? It meant a memory reference instruction. And if you remember, we had seen some, yeah, here you can see that. You can see these are the register reference in the there. Yeah. So if you remember, 000 was for AND, then 001 was for add, then 010 was for LDA. So all these memory reference instruction. That means if I give 000 here, if you remember, we needed to perform what? We needed to perform the AND operation, right?
Yes, ma'am.
So what is the job of this decoder? What is this decoder doing here? It is taking this 000 and activating the D0. As what is the job of this 3 cross 8 decoder? It will activate the 0th output whenever we feed 000 here. Now this 000 that we have given activates the 0th output, which is attached to, let's say in our case, if this is to perform AND, then it will be attached to AND gate. Okay, this for one output will be attached to, let's say, adder circuit. Okay, so whatever opcode we are giving in these 3 bits, corresponding output is activated. That means power is given to passed on to that particular circuit. Okay, so if 000 was given, then what circuit was activated? What circuit? And if 001 was given, then the adder circuit, for example, is activated, and the operands are taken from here. Yes, according to the mode bit. If it was a direct, then, or immediate, whatever mode is there, then accordingly the address is being supplied from here, right? This mode bit is being further transferred into a 1-bit memory element called flip-flop, which is supplied to the control unit as well. Okay, so that it can infer what is the meaning of this mode bit, and accordingly, decide what operation is to be performed. Is this clear? This upper half of this block diagram is clear to everybody?
Yes, ma'am.
Okay. Now we are going to look at the lower part. Okay, we are going to look at this lower part. Now what you see here is, first of all, a 4-bit sequence counter. Now what is a 4-bit sequence counter? Sequence counter is basically just an electronic component which is responsible for counting in sequence. Okay, so when I say that this is a 4-bit sequence counter, it means it generates the counting sequence 0000, 0001, 0010, 0011, 0100, and so on till 111. Is this clear? Is this clear?
Yes, yes, ma'am.
Okay, so that is the job of the sequence counter. Now please see why we are using this sequence counter here. This sequence counter is connected further to this 4 cross 16 decoder. Okay, now the 4-bit counting is generate कर रहा है ना ये. The 4-bit count, let's say 000 or 001 or whatever, which is generated by this sequence counter, is applied as input to this 4 cross 16 decoder. Okay, though that count serves as the input to this decoder, and accordingly a corresponding time signal is activated and sent to the control unit. In other words, when the sequence counter produces 0000, then this 4 cross 16 decoder has just received the input 0000, and it will activate its first output, which I am saying is T0, is clock pulse T0. Okay, or the timing signal T0. Next time when it produces 0001, then first output is activated and we say that a timing signal T1 is generated. And these timing signals go on till T15 and then return back to T0. Is this clear? Okay. Now, if you want to remind yourselves, although I have discussed this in detail with you, but if you still want to remind yourself what is a clock pulse and what is its important, then what is its importance, then we can just take half a minute and read through this screen again. Dipali, Can you please help everybody recapitulate what I've talked about the clock pulses so far?
Yes, ma'am, sure. The timing for all registers in the basic computer is controlled by a master clock generator. The clock pulses are applied to all flip-flops and registers in the system, including the flip-flops and registers in the control unit.
Remember that we had seen the clock pulses coming to all the registers, and I had told you that this entire system of registers, which we call together as the bus system, works together whenever a clock pulse is applied. Similarly, when we had seen the flip-flops, I had again reiterated this fact that this particular flip-flop will deliver the output only when this clock pulse is applied to it. You remember that?
Yes, ma'am.
Does anybody remember?
Yes, ma'am.
Right. So it is the same clock pulse that we are talking about. The only difference is that today we are seeing how those clock pulses are generated. Okay. So this is how those clock pulses are generated. This is the hardware for generation of a clock pulse. So there is a sequence counter which generates 0000, and correspondingly a T0 time signal is generated. Then it generates 0001 and the T1 clock pulse is generated. So if you remember, we had said that these clock pulses are applied to all the flip-flops and the registers in the system. Okay? And here then they are telling you that these are applied to all the flip-flop and register in the system, including the flip-flops and the registers in the control unit. So throughout the entire computer. Okay? Huh. The clock pulses, Diwali.
The clock pulses do not change the state of a register unless the register is enabled by a control signal. The control signals are generated in the control unit and provide control inputs for the multiplexers in the common bus, control inputs in processor registers, and micro operations for the accumulator.
Is this clear? Right? Is this clear?
Yes, ma'am.
Okay. These control signals I just told you about, these are the signals generated by the control unit. So you can see that these control outputs that you see here are what? These are the control signals. So the first thing that is applied to every unit in the computer system is the clock pulses. Okay. And the second thing that is applied is the control signal. So whatever circuit is to be activated, a control signal will be sent there. Okay. So only when that circuit has a clock pulse and a control signal, both, only then it will work. Is this clear? Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
Okay. Yeah. So let us just now read through this portion that I have just explained to you uh, in this description to make it more concrete. Okay, before we do that, there are three things that you see happening here. So please see this sequence counter is further connected with the system clock again. Okay, so what this system clock, what is the significance of this clock here? It will, we see the sequence counter will produce the next count only when it gets a signal from the clock pulse. Okay, so every clock pulse that you get, with every clock pulse this generates the next count, which is fed to the decoder and which leads to the timing signal. And that is how the sensitivity of this timing signal, how these timing signals are produced with the synchronously with the clock. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right. Now there are two other inputs here. One is the clear and other is the increment. Okay. So clear input is, suppose you want to, in between somewhere, you want to, the user wants to reset the counter before it reaches to, let's say, 15 or something like that. And increment is a simple increment operation. So if I want to, in between, somewhere, just increment the sequence counter, then this control input is used. Okay. Yeah. Can you please read from here the outputs of the, no, 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 the
Mm.
4-bit sequence counter. Here, the 4-bit sequence counter.
Counter can count in binary from 0 to 15. The outputs of the counter are decoded into 16 timing signals, T0 to T15. The internal logic of the control gates will be derived later when we consider the design of the computer in detail. The sequence counter can be incremented or cleared synchronously. Most of the time, the counter is incremented to provide the sequence of timing signals out of the 4x16 decoder.
Yeah,
Once, once in a while, the counter is cleared to 0, causing the next active timing signal to be T0. As an example, consider the case where SC is incremented.
sequence counter. SC stands for the sequence counter.
Is incremented to provide timing signals T0, T1, T2, T3, and T4 in sequence. At time T4, sequence counter is cleared to 0 if decoder output D3 is active. This is expressed symbolically by the statement D3 T4 colon equals counter pointing 0.
Yeah. So as I told you that in between, if we want to, for some reason, if we want to, uh, you know, uh, set the timing signal to 0 again, then we use the clear input. Now you will see in the next class onwards, you will see there are different. We will be looking at the implementation of the different instructions that I said at the beginning of the class. You will be performing in the CPU sim. So those instructions, their implementation is of variable lengths. So some instructions take more time signals to execute. That means they take more time to execute. And some are fast. Okay, some are smaller, right? So they take less time to execute. So obviously, it is not necessary for every instruction to require these 15 time signals to get completed. Okay, so some may only require signals up till T3, some may complete by time signal T5, and so on and so forth. So after the completion of each instruction, what would we like to do? We would like to set the sequence counter back to 0 so that it can start the timing signal T0 for the next instruction. Okay, you will see this in the next class when I start talking about the implementation of the instructions. So that is why there is a provision for clearing the sequence counter. Sequence counter is denoted by SC. Now, how do we write this down? So we simply say that sequence counter is getting the value 0. This means that we are clearing the sequence counter. What is the meaning of this? This means that we are doing this in time signal T4. Okay. And D3, when D3 was active, that means that the opcode here was 011 and the corresponding D3 signal was input. Okay, so this statement that you see here means that when the opcode here is 011, obviously then the third input, that is D3, will be selected, and the sequence counter is what? It will be 0100, because at that time T4 will be active. Yes, is this clear to
Yes,
you?
yes, ma'am.
Yes,
Right?
ma'am.
So when the opcode was 011, that is D3 was active, and the sequence counter has produced the count 0100, that is T4 is active. At that time, what do we want to do? We don't want to do anything here. We want to actually clear the sequence counter itself. That is, we want to reset it back to 4 zeros. Why? Probably so that we can start off the execution of the next instruction. So as you will see in the next class, this micro instruction that you see here, this generally marks the end of the instruction executions. Is this clear? Is this
Yes,
clear,
ma'am.
students?
Yes, yes, ma'am.
Okay, so today was a base class which, you know, dealt with several important concepts. We have discussed about the different kinds of control units. You have seen how the control unit is interacting now with the memory unit. For example, in the block diagram that we've just seen, you've seen its interface with one of the registers, that is the instruction register from this memory, right? And after after this stage, after this stage, then it generates control outputs which may lead to the functioning of one or more circuits. Okay, one or more circuits, which might be a part of the arithmetic logic unit. Is this clear? Is this clear to everybody?
Yes,
Yes,
ma'am.
ma'am.
Right.
Yes, ma'am.
We also revisited the concepts of clock pulses, and today we have seen how they are actually generated, how the timing signals are generated. Okay, and uh, we have discussed what is the difference between the two types of control unit, that is the microprogrammed control unit and the hardwired control unit. And we will be looking at the implementation of the hardwired control unit. Is this clear? Is this clear?
Yes, ma'am. Yes, ma'am.
Okay, right, right. So the next class is going to be very important because uh, whatever we're going to do is generally asked in theory exam also, and is also required to be done in the practical. Okay. So please try and attend the next class. Okay, 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 okay.